Well, hi everyone, and greetings from Northern Michigan. This is Bob the Science Guy. Today we're going to have a quick talk on telescope mounts. So I want to go over the operation of telescope mounts and the two major types, which is the altitude azimuthal and the German equatorial mount. And to do that, we're going to use a program called Stellarium, which is available free over the internet. Now, one of the cool features of this program is you can set the location, the date, and the time. I have this set up for Alma, Michigan, which isn't far from me. And it's 6:11 a.m. this morning. And what I want to demonstrate with this is that the sun is rising to the northeast of my location. So you see, here's east, here's sunrise, and as you see, it's clearly well north of due east from me. But let's go ahead and cue up the music and learn a little bit about how telescopes work and how we use them in backyard astronomy. So here we are in Stellarium, and we've got this set for today's date at a little bit after dawn, and we're going to go ahead and have a look and see how the grid system in the celestial sphere works. So the first thing that we're going to do is let's turn off the ground and turn off the sky. So now we see the star field that we would see if it was nighttime and we were looking north right now. Now what we're going to do is we're going to go ahead and turn on the equatorial system. Okay, so we have the northern celestial pole, which is the spot in the sky directly over the geographic North Pole, and it's given a designation of 90 degrees north. So we're going to start here, and we're going to find this star out here called Capella. Now, looking over on the information on Capella, we see that right ascension, 5 hours and 16 minutes, and the declination is almost 46 degrees. As we said, the northern celestial pole is at 90 degrees. So what we're going to do is we're going to drop the telescope down until we get down to about 46 degrees. Then we need to look for 5 hours and 16 minutes right ascension. This is the 6-hour line here. This is the 5-hour line here. And as you see, Capella is about a quarter of the way between the 5-hour line and the 6-hour lines. So we'll slew our telescope in right ascension up to 5 hours and a quarter. And Capella should be more or less in that general area. Now, what happens as the day goes on? So let's bring this down so that we can see Capella nice and clearly. So what we'll do is we'll go ahead and speed up time a little bit. Let's just bring it up a couple. Now, you notice how Capella is maintaining its distance from the northern celestial pole. It's still between the 5 and 6 hour mark, but the entire sky is rotating in a counterclockwise manner. That has to do with the fact that the Earth is rotating underneath the stars in the opposite direction. So, with us sitting here on the Earth, as we look up at the sky, it will appear to rotate counterclockwise in the northern hemisphere, and as we look south, it will rotate clockwise. So let's go see how a telescope mount accounts for this rotation and keeps Capella right in our eyepiece all night long. So let's go ahead and have a look at a couple of different telescope mounts. The first one is going to be the altitude azimuth mount. Now, this is a rather simple mount, and it's based on a swivel gun for a cannon. So the first thing that you want to do is imagine that the mount is sitting at the north geographic pole of the Earth, and the Earth will be rotating underneath it, but Polaris will always be directly above us. Okay, so here we have our telescope sitting at the North Pole. It's pointing straight up at the North Celestial Pole. Now, this is the first of two setting circles on a telescope. Now, with this setting circle, with the telescope pointing directly up, it's indicating that I'm pointing at 90 degrees. If I was pointing directly at the horizon, it would be reading 0 degrees. And that's how we determine what we call declination in astronomy. We start off at the North Celestial Pole, and then we increase our declination down to the horizon. Now, as you recall, looking from Stellarium, we had a circular grid system in the sky centered on the North Celestial Pole, and then as our declination increased, we had larger and larger circles. So in order to find Capella, what we will do is we need to go from 90 degrees down to 46 degrees, and that's a rather straightforward thing to do. So now it's set at 46 degrees. This will get us on the correct circle around the north celestial pole that we need to find Capella. Now we have to go along that circle until we get to 5 hours and 16 minutes, which is about 5¼ hours. Let's go down and have a look and see how to do that. Next, we want to find 5 hours and 15 minutes. Well, we really don't know what that is, so what we'll do is we'll rotate the telescope around until we find Capella in our eyepiece. It's very difficult to find where you are in right ascension, so I know that I'm at the right circle with 46 degrees. So all I do is rotate the telescope around until Capella is in the viewfinder. Then I adjust the right ascension setting circle until it reads 5 hours and 15 minutes. That just makes finding the next object easier because I know my declination circle is set correctly. Now I've set the right ascension circle correctly. Now we have a little closer look at the right ascension setting circle. I've moved it to 5 hours and 15 minutes. Now you notice that in the base there it says LX drive system. There is a clockwork drive system there that will rotate the telescope completely around in 360 degrees in 24 hours. So once I have a star zeroed in my eyepiece, I turn the motor on and the telescope will continuously track that as long as I want it to. But unfortunately, we do not live at the North Pole. We live at 45 degrees north latitude. So how are we going to set this arrangement up so that it works at our home? So what we do is we use something called an equatorial wedge, and that's this piece right here. We set it to our approximate latitude, and now the telescope is pointing directly at the North Star. To better visualize that, we can hold a globe up next to it, and we see that this plate is parallel to the equator of the Earth, and the telescope is pointing the same direction that it would from the North Pole. So basically, by putting this plate in, we make the telescope think it's sitting at the North Pole. And then we simply operate it in the usual fashion, moving it back and forth in declination and in right ascension. That is an equatorial azimuthal telescope mount. Now let's talk about a little bit of nomenclature. If we want to move the telescope up and down like this, we move it in declination. If we want to move it in this direction to follow a star, this is in right ascension. If we want to move the entire plate up and down, that's called changing altitude. And then if we want to move the entire plate east and west, we change our azimuth. So this is the actual mount itself. This is just a stand, and this sets it up so that it points to the North Star. So to line up the telescopes on the altitude azimuthal mount, we want this bar pointing directly at the North Star. On a German equatorial mount, we have the altitude axis pointing at the North Star. This is more designed for a piece of artillery, whereas this one is designed more like a surveyor's transit. It's a very precise way of doing it. This is good for big, heavy mounts. These are good for very light and precise mounts. So now this telescope would be pointing at the North Star. One of the keys to doing this is these telescopes need to be very well mounted. So we have the telescope and we have a counterweight, and it's designed so that when you let it go, it doesn't move. This has not got an eyepiece in it, which is why it moves slightly. But let's bring it around like this. Now to move the German equatorial mount in declination, we simply go like that. When we find our star, we lock it, and then the mount rotates counterclockwise to follow that star around the celestial sphere. Now once again we have our setting circle for declination here. And then these are our setting circles for right ascension. Both mounts have got a bubble level on them to make sure that the mount itself is level with the ground. So those are the basics of the German equatorial mount and the altitude azimuth mount. Now, in our next episode, we're going to talk about polar alignment. We'll probably tackle each one individually. And then we'll start working our way through backyard astronomy from there. So thank you very much for stopping by, and I hope you found some of this information useful. I went through a lot of YouTube videos when I was learning how to do this, and I always thought that I could tell the story a little bit better than I had heard previously. So I decided to make these videos. In our next episodes, we're going to talk about doing polar alignments, both manually and computer assisted on both these telescopes. So in the meantime, this is Bob the Science Guy signing out from Northern Michigan. Thank you very much for stopping by. Make sure you hit that like and subscribe. We do have Patreons and memberships, and I've got a new store if you'd like to click on that on the main channel. So until next time, see you later.